Hello everyone. So how about let's start today's. So looks like that we have a little less people than usual, but it's fine. Alright, so hello everyone. Welcome back to ACSL. And this week I plan on trying to teach two lessons since we're a little behind on schedule. So everyone can hear me clearly, right? So let's see. So just like I said before, I'll try to teach two lessons today since we're a little behind on schedule. So our first one would be Boolean algebra. So so what is Boolean algebra basically? So Boolean algebra is just a branch of algebra. So algebra is just talking about variables and solving those variables. And in Boolean algebra, there's actually only two values, true and false. And it's usually represented by ones and zeros, respectively. So let's first ask what is even a Boolean? What is Boolean? So Boolean is just a simplest piece of data that can exist and that there's actually only two possible states that could be in. Either it's in true or either it's in false. So just like I said before, they are represented by ones and zeros. So true is represented by one and false is represented by zero. So a single Boolean value can also be represented in a bit since our computers and our technology is designed to work with bytes instead of bits. Okay, so we can sort of think of Boolean algebra or Booleans as sort of like a switch, an on switch and an off switch, or a true or a false and a true. So these switches, when we interpret them, then they'll just give us an output, either if it's a true or a false. So why are Booleans so important? They're important because in because all electronics store data as bytes, as I said before, and one byte is a collection of 8 bits. So the operation of these bits is basically the most basic and the most foundation of computing. And a synonym, or sometimes we'll see Boolean logic as logic gates as well. Right here is just a very simple version of how it looks when we add Booleans. Okay, let's go into the actual Boolean algebra part. So for just like in math, we have operators and Booleans. And it's actually quite short and not that long, and there's only three main operators. Our AND operator, our OR operator, and our NOT operator. So has everyone seen a graph that looks like this? Or something called a Venn diagram? Yeah, so basically we can represent our booleans with a Venn diagram. So for our first operator, it's just AND. It's just basically talking about the middle, where the two circles overlap. And then our OR operator would just be talking about anywhere in the inside of these two circles. And our NOT operator is just anywhere that's outside of our circle, or it's just basically talking about the opposite of our values. I'll go into more detail as we move on, as there are also slides that explains it more in depth. So for our Boolean algebra, we have truth tables. So our truth tables usually only have two values, an A value and a B value. So these is what we call ordered pairs. And they're usually either zeros or ones, or just like how in previous slides, or false and true. So a note to remember is that usually we have two, but it's still possible to have more than two. But having more than two values are just rare, so we just focus on two values. So sometimes we might have three values called order triples, or four order quadruplets. And then for these, we it just increases the amount of possible combinations. So with only two values, we only have four possible combinations. With three, we have eight possible combinations, and four, we have 16 possible combinations. So there's sort of like a pattern that we can sort of see as we move on. So like where there's five values, there's also how many possible combinations. It's just a pattern. But we're just focusing on two values since that's the most common and what we usually see. Okay, so welcome, new people. So today we're just talking about Booleans, and we also have one more lesson that's we're a little behind the schedule. So let's.
Excuse me.
Yes.
I was late, so can you tell me what happened, please? Thank you.
Yeah. So basically, I was just explaining the uses of our Booleans and our Boolean algebra. So Booleans is just talking about how it has two values, a zero and a one, or true and false. So our false is represented with a zero, and our true is represented with a one. That's basically the most important things that you would need to know. So, and there's also operators, just like how in math, we also have operators in Boolean algebra. And we have three main operators. Our first operator that we're going to talk about is our AND operator. So our AND operator can be written as xy or just x times y. We can actually think about it like multiplying zeros and ones. So here, just like how I said before, our Venn diagrams are here, and our AND is represented by the part where they both overlap. So x and xy, or x times y, or x and y, will only return true or 1 when both x is true and y is true. So this right here was what I was just talking about in the previous slide, which is a truth table. So for our x and y values, these are all the possible combinations of zeros and ones. So we have the possible combination of x is 0 and y is 0, x has 1, y is 0, x is 0, y is 0, y has 1, I meant, and x and y both as 1. So for an operator, where it will only return true or only return 1 when they're both true. Since we're trying to look for which ones are in the overlapping spot. So for false, it's just basically talking about it's only by itself. Since Venn diagrams, we're usually using for comparing and contrasting. So the overlap spot is where they're both similar, and the non-overlapping spot is where they're both different from each other. So when it says false, we're just talking about this open space right here. So that's why when we have our first one, 0, 0, or false, false is just talking about these two white areas. And since they're not in this red area, so it returns as a false. Our x is in this middle area, but our y isn't. So it will return as false since they're both not in this area. So basically, the main idea is that our xy will only return true, or x and y will only return true if they're both true. All right, so far so good. Any questions? Uh, Tell me if I'm going a little too fast since I'm trying to teach two lessons today, so I might go a little fast. Alright, so our second operator would be our OR operator. So our OR operator is represented with a plus sign. So just like before, we also have a truth table here for our OR operator, and our OR statement will only return true if x is true or y is true. So in our truth table here, it's just like before, we have all the possible combinations. We have false, false, true, false, false, true, and true, true. We can sort of imagine it like adding, except for the last one, since 1 plus 1 is 2, but it's just 1. So basically, we either x is true or y is true, then they'll return true. So you see before, if x was true and y was false, it'll return a false, because that was our AND one, where they both have to be true. But for our OR operator, only at least one of them needs to be true. So if x is true, then but y is false, it'll still return true. Or vice versa. If our x was false and only our y was true, it'll still return true. But if our x is true and our y is both true, it'll still return true. Since it just needs at least one of them to be true. So is there any questions about our and or operator?
Uh,
Okay, so let's move on to the last operator that we need to know is our not operator. So our not operator is both sometimes shown as this weird L shape right here, or sometimes also shown as like a squiggly line. Let's see. So it's not on the slide. I think it's on the key. It's okay. There's examples of it later. So yeah, so our not is just basically talking about the opposite. So not x is always just the opposite of x. So if x is false, then not x is just true, the opposite. Or if x is true, then not x is equal to false. We just think of it as true and false as opposites of each other, just like how on and off was. Right. So yeah, so the not operator is actually pretty simple. It's just basically talking about the opposites. So we have four types of simplifications. We have our commutative property, associative property, and distributive property. But then we,
um, I have a question.
yeah,
Can I see the slide before?
sure. By the way, these slides I'll also be posting them on the Google Classroom after class. So if you guys aren't able to write it down, it's okay. You guys can always reference the Google Classroom. Okay.
Okay, thank you.
Yeah. So basically, as I was saying, we have four types of simplifications or properties. So our top three, I'm not sure if you guys have seen it in school yet. Have you guys seen these top three at least, or remember it? It's okay if you guys don't, because I'll be going over them. Yeah. So the little more the special one would be our fourth type, which is our the Morgan's law, which I'll be also explaining. So first, I'll go over the first three, which is just talking about our commutative property, which is just talking about where we can add or multiply in any order. In this case, instead of just saying add or multiply, we have our or and. So like in our example down here, so 3 plus 5 is equal to 8 is the same as 5 plus 3. So it doesn't matter what order we add them or we multiply them. Our next one would be our associative property. It just means that we can also just group them in any way we want. So we can group A and B together, or we could group B and C together. It doesn't really matter since it will always be the same. So we can always just group them differently. So in our example here, so when we group 2 times 3 and then times 4 on the outside, it'll give us the same as just 2 times grouping of 3 times 4. So this is just our associative property. And lastly, our distributive property. So this just talks about how we can distribute a multiply on the outside into the parentheses on the inside. So for our example right here, 2 times a group of 3 plus 4, if we break it down, it's the same as if we distribute it. So 2 times 3 and 2 times 3 plus 2 times 4 is the same thing. This will be our distributive property. Okay, so time for our special law, which would be our De Morgan's law. So the Morgan's law is kind of like the distributive property, just a little bit different, as it shows not as distributing to the operators. So in De Morgan's law, we assume or and are opposites of each other, just like positive and negative, on and off. So when we distribute our not into our A and B, it will turn into our not A or not B. It will turn our and into its opposite or. And it will happen the same thing with our or operator. So if there's a not, when we distribute it, it will be not A and not B. It will just change our operator into its opposite operator, or to and to or. Is there any questions about the Morgan's law since it's a little bit more new and we don't really see it in normal school? So no questions, then let's move on. So these are just some extra simplifications. So a or 0 or a or false is just going to be equal to a. A and 0 or a and false is just going to give us false or 0. A or 1 will just give us 1 or true. A and 1 will give us an A. A or not A. Yeah, this is the squiggly line that I was talking about. This also represents not. So A or not A would just give us 1, which is true. A and not A will give us 0, which is false. A or A would just give us an A again. And same thing with A and A. It would just give us A as well. And lastly, not A would just give us A. They're just some extra simplifications, and that it's good to know them. So yeah, just as I said before, I'll put the slides in the Google Classroom, so you guys can always take notes there. But alright, my bad. So I'll move on, and you guys can always just copy this down in the Google Classroom. Since after class, I just post them into the Google Classroom, so don't be afraid. I just need to move on because there's also one more lesson that I'm trying to teach. So let's move on. So another type of Boolean algebra problem that you may be asked is if two equations are the same, or if two equations are equivalent. And they're only the same if the truth tables match and are the same. So there's an example on the next slide. So we will prove the Morgan's law works by using our equivalent statements. So remember, our the Morgan's law is distributing our not into a group of A and B, or A or B, and it'll just flip the middle operators. So not A or not B, not A and not B. So can you guys tell me which ones are the same or which ones are equivalent? Basically just type in the chat. So this would be 1, 2, 3, and 4. It's okay if you don't know. So basically our column 2, 1 and 2 are the same. And then our columns 3 and 4 are the same. So they're the same because if we look at the truth tables, they exactly match. There's 0 on the first one, 1's on the second one, 1's on the third one, and 1's on the fourth one. So if their truth tables are exactly the same, then they are equivalent or they're the same. So do you guys want me to like go through this or so let's just move on. So another one would be tautology. So it's just talking about how if any value of A or B is just gonna return true. Like A or 1 is just equal to 1, and A and not A is also just gonna return 1. Just a little concept. vocabulary. So let's try a little practice. So let's see if this statement is true or false. I'll give you guys like 3 minutes to try this. So false is equal to 1 and true is equal to 1 and false is equal to 0. So we will just solve this using mathematics and see would this return a true or would this return a false. Uh, so how about we walk through this step by step? So our 3 plus 4 is greater than 6 is true because when we do the math, 3 plus 4 will be equal to 7 and 7 is greater than 6, right? So this will be true. Now let's move on to our other one. 7 minus 2. This will give us 5. And 5 is actually not greater than 6. So this will return a false. False. So when we have true and false, it's just equal to false. Since for our AND operator to return true, we need both the first one to be true and the second one to also be true. So the answer for this one would be false. So we have also practice number 2. This one could be a little harder. So basically, just like, so we use this in mathematics, so we would just solve all the math normally, and then also apply all our Boolean algebra operators. So I'll give you guys like 1 minute, 2 minutes, 3 minutes. So how about we walk through this step by step? So, oh, I'll pop that once. This guy. So let's first solve the inside parentheses, our math. So it's just the same. These two are just the same as our last problem. So 3 plus 4, that will give us 7. And 7 is not less than 6. So our inside would be false. But since we have a not on the outside, it's the opposite of false. So our first one here would actually give us true. And for our second one, we have 7 minus 2. And this will give us 5. And 5 is not greater than 6. So this is false. And in our parentheses right here, so we would have true and false. And this would return us a false, since for our and to return a true, we need both of these to be true. So if it's true and false, this would just return us a false. So our first part gave us a false. Now let's move on to our second part. So we first do our math operator, which is 5 plus 1 is equal to 6. And this is true. So this is the same as not parentheses true. And because we have a not on the outside, it would just turn it a false. So then in the end, we have false or false, which would just return us false. Since in order for or to be true, it has to at least have one true. Uh, So is there any questions about Boolean algebra or or things that I should clear up? Yeah, I'm okay. So, is there any questions? If there's not any questions, I'll move on to the second lesson. So, is there any questions? Just double checking and making sure, because I think I went through that a little fast. Uh, so that's good. So everyone understands Boolean algebra. Remember, if there's any questions, it's all you guys can always just ask in the Google Classroom. It's not too late. Okay. So let's move on to this. Alright, so for our second lesson that I'm gonna teach today, it would just be our last lesson. We were supposed to teach this lesson for the whole class today, since we're behind the schedule, I'll actually teach both of them today. So let's move on to our last topic that we need to learn. So our last topic would be our graph theory. So just as I said before, this will be the last topic of this class. And if there's any slides or specific things that you guys want me to go over, you guys can always ask in the Google Classroom, and I can always just post the slides. So let's go on to graph theory. So this is a little table of contents. So we'll have a small introduction, then we'll talk about what is graphs, kinds of paths, a little recap of vocabulary that I'll be talking about. We will talk about transversability, and then in the end, that's basically it. So let's first start with our introduction. So in ACSL, graph theory is usually going to be tested in reading graphs, drawing graphs, and finding paths from one point to another. So let's so we so some people may ask, why is it useful? So graph theory can actually be used in a lot of things in real world, like at least the network. And like some examples could be like how our school rooms and hallways are connected, or how a friend group could be connected. Like you're friends with Bob, or Bob is a friend with Joe. It's just talking about a network of things. So what is a graph? So in school, we might think of graphs. The first thing that we probably think of is like coordinate planes and lines and stuff. But in ACSL, our graph is probably looks like this. So our graph is made of nodes or verticals, and that's connected by edges. So a node or vertical is a point like these, and they're usually represented by an uppercase letter. Like in this example, in this graph right here, it's represented by like A, B, C, D, and E. Our edges are the lines that connect our two verticals or nodes together. So let's say node A and node C. This line right here, this will be our edge. So when we define a graph, our nodes and verticals are defined like this, with commas and single uppercase. So our A, B, C, and D. Our edges of our graph are represented by two letters. It's just talking about which two nodes this edge is in between. So like the first one would be AB. So we'd be talking about this edge right here. AC is just talking about this edge right here. AD is talking about this edge right here. And lastly, DE, which is talking about this edge right here. So it represents a path and is connected by an edge. So this would be a path. That's what we would call a path. So good news is that in elementary division, these graphs are only undirected graphs. So that means that they can go in either way. That means if you either go from A to B or B to A, and it will be the same thing. While directed graphs, even though that we won't use them, it's just talking about how only go in one direction.
I have a question.
Yeah.
I don't understand this. I don't think I get it. This graph thing.
Yeah, it's okay. So I just went through a little basic vocabulary and how we have nods or verticals and edges. Our nods or verticals would be our dots or our points, and our edges would just be our lines. Our edges is just the thing that connects two dots together. So we would define these and assign these with brackets, with these squiggly brackets. So our nods and verticals we will assign with one letter. Our edges we will assign with two letters. And edges are also our path. So basically, I was just talking about how undirected graphs, and it doesn't really matter what direction it goes, so it can go from A to B or B to A, and it'll be the same thing. So is there any more questions so far about vocabulary? No questions? Then let's move on. So what are we now? Let's move on to kinds of paths. So we sort of have a table right here, and we will use this graph as sort of like a visual. So let's first go down the path or graph. So we have AB. AB is just talking about how the edge between our knob A and our knob B. So just this has a path length of 1. And then we have, as we move down the table, we have our next one, which is BCEF. So this is just describing the path that we have from node or vertex B to node or vertex E. So we could see this as like a step by step. So we first go from B, and then we'll move to C. After that, we move to F, and then down to E. That will be our path. So this path has a length of 3, as we can see. So B to C, that's a path length of 1. C to F, that's a path length of 2. And then finally F to E, this is our third path length. So BCFE has a path length of 3. Something like ACDEF is not a valid path since we skip our B. So can you guys just type in the chat and tell me two paths that we can get from vertex A to vertex F? Yeah, so I saw some Answers? Yeah, so basically our two paths would be A to D, A, D, E, F. So that'll be our first one. And then our other one would be our A, B, C, F. This would be our two paths. Since in order, we need to put them in have a path length of one. So A, B, C, F, and A, D, E, F. So does everyone understand how graphs work so far? Uh, let's move on. So now we move on to some path terms, or mainly, so we have a simple path and we have a connected graph. So a simple path is just talking about a path that does not repeat our verticals or nodes. So our A, B, C, F would be a simple path since we only go over these nodes once. But our second one, A, B, C, D, E, F, A would not be since we go over A twice. And then a connected graph is where a vertical or node have a path to all of the verticals and node. So is the graph below a connected graph? So a connected graph doesn't need to have like a direct jump to all of them. So as long as it's possible to get to all of them, then that would be a connected graph. So our next kind would be our diagonals. So our diagonals is an edge that just connects two verticals and nodes that are non-adjacent in a polygon. So does everyone know what a polygon is? So I do see some yes and I do see some no, and that's okay. So basically, a polygon is just talking about a two-dimensional shape that is drawn by using straight lines. So this one would be a polygon, as it is only drawn by straight lines and it is a closed shape, closed two-dimensional shape. So this would be a polygon. So our diagonals would be an edge that connects two that are non-adjacent to each other or not next to each other. So B to C would be a diagonal, A to D would be a diagonal. And since ours is unidirectional, so that means A to C is the same as C to B, A to D is the same as D to A. Our diagonals would be our pink lines, and our edges from before would be our green lines. All right, so a universal rule would be every connected graph has this following relationship. Edges is equal to our verticals plus our diagonals. So let's test it. So remember our edges is just talking about all lines that all lines that connect our knobs together. So that means even diagonals would count as edges too. So this one would also, our first question would be to ask, is this a polygon? Which would be yes. And then we would count the number of edges. In this case, it would be 1, 2, 3, 4, 5, 6. So you get our 6. Our verticals, or our knobs, which is our dots, which would be 1, 2, 3, 4. So give us our number. And then finally, our diagonals, which is 1, 2. And then according to our equation right here, our edges should be equal to our verticals plus our diagonals. So 4 plus 2 would give us our 6. So just type your answer in the chat. So is our bottom shape here a polygon? Remember, a polygon is just a closed two-dimensional shape that is drawn with straight lines. Okay, yeah, so our bottom shape here would also be a polygon. So that means let's also test our equation. So we will first count our edges, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 edges. And then now let's count our verticals or our knobs, which is our dots, which would be 1, 2, 3, 4, and 5. So we have 5 verticals. Now let's finally count our diagonals, which we have 1, 2, 3, 4, and 5. So we have 5 diagonals. And then we just plug into our equation. So if it is a connected graph, this equation should be true. So our edges should be equal to our verticals plus our diagonals. In this case, we have 10 is equal to 5 plus 5, which is 10 equals to 10. So this is a connected graph. Is there any questions about identifying if something is a polygon, counting edges, counting verticals, or counting diagonals? Okay, so let's continue. So there's also a path called a cycle. So a cycle path is where our starting point and our ending point is the same. So our example right here would be A, B, C, A. So if we follow it, we have go A, B, C, A. So this would be a cycle because both our starting point, we start with A and we end with A. So a thing to note is that our verticals must be written in the order that they move in. But our vertexes or our starting and ending points could be in any order. So that means that ABCA, BCAB, and CABC are all different ways that we can write a cycle. So just like before, okay, let's test these two out. So we have B, we go to C, and then we go to A, and then we go back to B. So this would be a cycle. And then we have our C, which would go to our A, our B, and then our C. So this will also be a cycle. So this would be true. So since we're working with an undirected graph, a cycle has to be greater than or equal to 3 unique verticals. So we have to go out to at least 3 knobs. So for us here, we can't just do ACA. This that would only be this that would only be 2. We also need to do B, so A, B, C. Since now we have 3 different knobs. So then that will count as a cycle. Is there any questions about cycles? So let's continue. So let's have a short little vocab recap. So our verticals and our knobs, it's the points on our graph, and that they're labeled with an uppercase letter. Our edges, which is the lines that connect our verticals and knobs, a directed graph we don't use, but our directed graph is just telling us what direction. We can only go in one direction, but we won't use this, so we can just ignore this. An undirected graph is where we can go in both directions. So AB would be the same as BA. Paths are represented by a list of these nodes and that they represent the order that they move in. A simple path is just talking about where no nodes or points is repeated. So an example is like A, B, C, A. Since A is repeated, this is not a simple path. But ABC is a simple path since they all only appear once. A connected graph is a graph where all nodes can go to other nodes by some sort of path. And lastly, what we just talked about are cycles, where our starting point and our ending point is the same. So in our example right here, it will be B, A, C, B. So this is a cycle as our starting and our ending is the same point. So is there any questions about vocabulary? So now let's talk about transversability. That's good. So a transversable graph is just basically talking about if you can or you can't use every edge only once in a single path. An example of this could be the seven bridges, the seven bridges of Königsberg. It's a famous problem and from real life, and this problem resolves around the transversability of a graph. Euler's path it uses the degree of all verticals and our nodes. I'll talk about how we find the degree later. And we would use that to determine if the graph's transversability, or if every single edge can be used exactly once in a single path. So how do we find the degree of a node? So a degree of a node is just talking about the amount of paths that is coming into or out of a single node. So here we have our vertical A. So it has a degree of 4 since we have 4 lines coming out or into it. So that makes it have a degree of 4. Our vertical B has degree also has a degree of 4, as there is 1, 2, 3, 4 lines that are coming into or out of B. So just type your answer in the chat. So what would the degree of vertical D be? Okay. Yeah, so the degree of our vertical D would also be 4. Since we have 4 lines, 1, 2, 3, 4, that's either coming into D or out of D. So for our Euler's path, it is only if the amount of odd degree is 0 or 2. Odd degrees though, remember. So if it's even degree, then it doesn't matter. We just look at the odd degrees. So we would count the degree of every single node. So after we count all of these nodes, we will find that they all have a degree of 4. So we have 5 even degrees and 0 odd degrees. So if we have if we have no odd degrees, or if we only have 2 odd degrees, then that's a Euler path. So that means this thing, that this polygon or this graph has a Euler path. So one odd vertical means that zero odd vertical summit means that the earlier path can start at any vertex or any point, while two odd vertices means that the earlier path can only start and end at one of the vertices. So zero means that we can start anywhere, and that there's a path where we only use each edge once. Okay. Yeah, so that would be all of the lessons, and that would be graph theory. So is there any questions about graph theory or even about our Boolean algebra? Ah, okay, that's good. So remember we have a mock test next week, so remember to study for it. And if there's anything that you guys don't understand, you guys can always just ask us questions and we'll answer them. We'll try to answer them as quickly as possible. So it's basically almost time. So I'll let you guys go a little earlier since we're finished the lesson earlier. And remember, and always feel free to ask questions, all right? So thank you everyone for attending today's lessons and see you guys next week. Remember to study for our mock test.
Thank you.
Bye.
Bye.
Thank
Thank you
you.
for attending.